Okay, I think it's 11, so I think we can start. I'm going to apologize upfront that I'm going to have this cup in my hand because my throat is a little sore, so that'll help me actually speak more clearly. So as you saw in Prasanna's talk, so he gave you an overview about fairness and also the toolkit. What I'll do is that I'll give you a brief overview of the field of explainable AI in terms of what's being done. And then I'll jump to our toolkit, and I'll give you essentially a brief tour of the toolkit, show you some notebooks, and then we'll talk about some future directions and so on and so forth. Okay. So the first question is why, right? Like why do you need explainable AI? So one of the most sort of standard reasons, or something that also Prasanna mentioned, was that you need it for trust. So I mean, essentially, many machine learning and AI models are used across many high-stakes decisions for taking high-stakes decisions, and you want to know why certain decisions were recommended. So this is the most sort of obvious and easy to see application. So you have questions like, is it fair? Is it easy to understand? Can someone tamper with it? Is it accountable? And so on and so forth. So not just in terms of this, explainable AI has gotten a lot of traction, not just in the research community, but across industry and across various facets of society. Also, the media has jumped on various aspects of explainable AI and saying that we actually need explainable AI. So one of the reasons that this sudden need has sprung up, I mean, there were methods and there were things, systems essentially that wanted explanations, but there's been a sudden surge in this requirement, and the reason is mostly this. It's because of deep learning and the proliferation of the use of neural networks. So if you use, say, before a decision tree, in a sense, you wouldn't need something that actually generates explanations from it, because it's pretty obvious how the decisions were made. But if you have something like on the right, you probably need something that at least is able to dissect some aspects of how certain decisions were made. So the GDPR in Europe also says that not necessarily the most accurate, something doesn't have to be extremely detailed just to be accurate and no one understands, but rather have something at a level of abstraction that most people will understand and is meaningful in some way. Now, what meaningful means is, I guess, is left to one's sort of judgment in terms of what someone might say is understandable. So besides trust, though, are there other sort of motivations for having explainable AI? So one thing is simplification. So for example, so there was this thing that I'd heard about this work where they had built this humongous neural network, which essentially classified proper code from malware. Okay, and it was really accurate. It had, I think, an accuracy of 98% plus, and everybody was thinking, okay, this huge network has identified some really complex sort of patterns that otherwise would be sort of imperceptible, and so it's doing well. But then there was a group of people who thought, okay, let's see what this thing is trying to do. And what they figured out is that 99% of the neural network's performance just came from checking if the code had comments. Because presumably, if you have malware, you won't be spending time commenting the code. So this is an application where essentially you can see that simplification. Now, obviously, you wouldn't want this neural network to check malware once you know this. But there may be places where this one-liner might be something that's desirable. But now, rather than having to essentially use this really complex thing, you can just use a simple rule, which more or less has the same accuracy. The other thing is in debugging systems. So there was this incident with self-driving cars, I think a few years back, where they found that there was this car, I think a Honda or something, where they had put in this new braking system. And they found that the car would, when it saw a red light, it would slow down, but it wouldn't stop. It would just keep on going. So they were wondering why this actually happened. And on further investigation, it turned out that essentially the braking system, the brakes, were used in a different car, like a Tesla. And what used to happen is that when it saw a red light, it used to slow down, and then there was something called as a lurch, which would kick in. And what the system had learned is only when you see this lurch aspect, you actually stop the car. So when they actually put it in a different car, this lurch thing was absent, so it just kept on going, though at a slow pace. So the thing is that if you have ways of disentangling and seeing into systems and figuring out new things, you can try to uncover these sort of systematic errors. The other thing is like confounders. So there was also a study where there was this medical data set where people were trying to predict diabetes. And one of the things that came up with the model was that if you have pneumonia, then you won't get diabetes. I mean, I'm no medical expert, but there's very little relation between pneumonia and diabetes. The reason this was happening was that people who had pneumonia were presumably going to the hospital. And so since you went to the hospital, you get all these millions of tests that are done. And one of the things was they were checking for diabetes and sugar levels and so on and so forth. So most of the people having pneumonia did not have diabetes. But if you had data collected which said pneumonia, you had another column which said diabetes, yes or no, you would find that there's a high sort of negative correlation. So things like that. So the actual thing was, if you had pneumonia, you would go to the hospital. This aspect of going to the hospital was missing in the data. So you can essentially try to uncover these kind of confounding effects. Last but not the least, you might have a model that's highly accurate, but in most sort of decision making, such as in industry or even in other high stakes applications, there's usually a person involved that actually makes the decision. So it might be that you have a really accurate model, but if the person does not really understand the model, he might not, essentially, he either may not trust the model, or he may essentially trust it at wrong, he may trust it when he should not trust it, and so on and so forth. So in such cases, it's actually better to have maybe a suboptimal model that the person understands, because the final thing that you're trying to optimize is the model and the person and the final decisions that are being made. So if the person understands what's happening, it might actually lead to better on-field performance. Okay. The other things sort of explainability relates to is also fairness, because you can, if you have good explanation techniques, you might be able to uncover certain decisions that were unfair and so on and so forth, because you can uncover reasons for why certain decisions were taken. And robustness and generalizability are also other things. So, and all these are required for sort of widespread adoption and essentially deployment in real world systems. So the interesting thing with the wolf picture there was in terms of robustness, I don't know if Prasanna spoke about it, but there was this classifier that was essentially very accurate in predicting a wolf from a dog. So people thought, okay, let's see what sort of unique features of a wolf it's able to use to sort of distinguish it from a dog. And what happened is they figured out that essentially most wolf pictures occur in snow and dog pictures occur without snow, so it was basically just detecting snow. So it was just a snow detector. So this is quite a common story. So you need all of these things for essentially widespread adoption, because I think in real life, what we strive for more is robustness than optimality. This is an interesting article, where Geoff Hinton basically said that you don't need explainable AI, and there's some good points. And there's an article where some people sort of responded to him, but it's something I think everyone can think about. Do you really need it? I mean, what are really the core issues? What do you really need for building systems? So we can have a discussion maybe later on this, but it's something to look at. Okay, so now what I'll do is I'll do a brief review of certain more popular, arguably more popular types of explainability methods. I'll also show you a taxonomy that we have built based on knowing this space and in terms of what categories of methods that are there. And we hope that the taxonomy is also helpful for people, for practitioners, to essentially use and navigate to the right set of algorithms or class of algorithms. So I think this is a slide which Prasanna also showed. So you can have different types of things. So you can have directly interpretable models or post hoc interpretation, global versus local, as well as static versus interactive. So I'll touch a bit on each of these. So directly interpretable is just like a decision tree where the model itself tells you what's happening. Post hoc interpretation is required where you don't have this luxury and you have something that's essentially hard to figure out, and so you need something else that actually tells you what's happening. Global is that you understand everything in terms of the overall flow of the decision making, while local is just per instance you're asking questions and trying to understand, while static and interactive I think are kind of self-explanatory. So static is more like one shot, while interactive is something that sort of goes back and forth. So this is, like I said, is an example of a directly interpretable model. So you can have decision trees or rule lists. There are a bunch of others, but these are some examples where it's clear how the decisions were made. In a certain sense, even if you have bigger decision trees or rule lists, as things get more complicated, some people might argue, is that really interpretable because there's so many rules? So in that sense, I would say that they're more sort of directly transparent because you know you can follow the flow, but they may not be necessarily sort of consumable by you directly. So for post hoc interpretation, like I said, even before deep nets were popular, I think most people working in the industry would know this, that if there was any automated system, most sort of automated systems that did any kind of complex reasoning is usually an ensemble of different kinds of models. So you might have business rules, you might have some model that learns over the data, you might have statistical tests, and so on and so forth. So in all these cases, even though you may not use a deep network, you might still want to know, like, what is the system trying to do? And in all these cases, post hoc interpretation is one way of sort of getting at it in terms of building some other algorithm that is able to somehow sort of disentangle what's happening. So for local post hoc interpretation, this is one of the most sort of simple and arguably most popular algorithms out there. And it's called LIME. And what LIME does is very simple. So if you have this very complex sort of decision boundary shown by the light pink or whatever skin color, the thing is that you don't know what's really important. But what it says is that people are usually interested in specific decisions, so like the bold-faced plus sign. So I want to know, say, for example, a patient, why was I diagnosed with some kind of disease? So I'm basically interested in my case. So then what LIME does is that it'll take your case as well as it'll take a bunch of points around that case, and it will fit a linear model that is sparse, that is basically it'll only choose few features. And what they say is that this local sort of linear model, since it more or less approximates the boundary of the complex model, because in terms of performance, I will use this local linear model's features as an explanation for why I was diagnosed with this disease. So that's the basic idea. So you take basically your model, you ask for which point you want essentially an explanation, you generate a bunch of points around that point, and then you train a linear model on the predictions of your complex model for all these points. And you use the coefficients as explanation. So this is a very simple method, but is one of the first ones in recent history that came up with this idea of creating explanations in a post hoc fashion. Yeah, if you have any questions, by the way, please feel free to interrupt and ask. Yeah, go ahead. Right, so that's all, yeah, so that's all art in the sense that they choose like some 5,000 points, and What they do is usually they won't choose 5,000 from the data set. They'll take your point and they'll just like perturb it a bit. So perturb each feature a bit so that it creates new points that are not too far from the, because otherwise it could happen that you choose 5,000 and 2,000 of them are really far away. So although even though you might do that, it still may not be like the best method because it's a very loose coupling, right? Like you have your complex model, you get its predictions and you fit this line. I mean, it may match in performance, but who knows if that's what your original model is doing, right? You just hope that it is doing. So there are also like post hoc interpretation methods which are unsupervised. So say you're given a data set, like a complicated data set, and you want to understand this data set in terms of what's there. So you might want to select a few samples that are representative of the data set and essentially give you some idea. So for example, here, like if it's like a dog's data set, it might essentially select sort of different breeds of dogs. And it can also tell you like essentially instances in the data set that are at the boundary. So for example, like a dog with a scarf, right? I mean, that's very unlikely to happen. But so you can also have, so there are also these methods which can be used in an unsupervised sense. For images, one of the first methods that came up was called saliency maps, and the idea is very simple. What they do is basically they want to see that if you have a classifier, they want to see which inputs, if you perturb a bit, will produce the most change in your output class probabilities, because then those inputs probably have the highest sensitivity and are most important in essentially classifying. So for example, if it's like an image of a boat, this heat map that you see, the white part, it's saying are the features that are important in identifying the boat. And similarly for the other things. So it will basically create heat maps, and it says that this heat map is essentially an explanation. It's saying this is basically where the model is looking, and this is what it is doing. So this was one for images, which is again very popular, or was popular. So now you can have also a post hoc global interpretation, so where you may not be satisfied with just sort of per instance explanations, but you might want to understand the global structure or how things are done. So one of the most sort of natural things here, and this was done even before deep learning in terms of model compression and so on and so forth, is that it's kind of a similar idea to Lime, but you do it at a global level. Essentially, what you do is you have your complex model. You take the model that you think is interpretable, say maybe a shallow decision tree or something. You take a CART algorithm, say height 5, and you basically just train on the predictions of this complex model for your whole training set. And now, in many cases, it was observed that training this small decision tree on the predictions of the model actually made it more accurate than training it on the original labels. So now you use the tree as a sort of a proxy for what's happening in your original model. Now there are for all of these cases, there are methods in the toolkit that we have that are kind of, in a certain sense, more advanced. So we have some work here where rather than using the predictions, we do some reweighting of the training set, which was published at NeurIPS last year, and which we showed actually had some operational significance. So there are many methods here where you want to basically improve the performance of a simple model of choice. And this is a very very relevant use case, because, so one of the things I was involved in was with chip manufacturing engineers. So I used to like go every week and meet with these engineers, and basically we wanted to build tools that would help them and machine learning to help them. And the thing is that you might have the most accurate black box model there, but the engineer's like job depends on what happens. So he's not just going to like deploy something, even if you show extremely high accuracy. He really wants to know what's happening, because if something goes wrong, he has to explain to his boss like what's gone wrong. So in this case, we were actually, the original model was a neural network, and we had a tree model, and we were able to, with our method, improve the tree model significantly, so that you could just use the tree instead of the Then there are also, like I said, other methods in terms of like interactive, static or interactive ways of doing things. So in terms of visualizing intermediate layers of neural networks and seeing, say, for example, if you're training something on cat images, you try to see if intermediate layers somehow sort of capture certain aspects of the cat. And you use that as some kind of assurance that the model is actually picking up on things that it should be picking up on. So there are methods which do that, where you can just visualize intermediate. Okay. So like I said, so there are many explainability methods, and there's no single sort of definition of what a good explanation is. And it's really, it just depends on the domain, the person or the expert you're talking with, and so on and so forth. So for example, like if you have a loan application, right, and you have applied, and say your loan is denied, you just care about why was your loan application denied. But if it's essentially a loan officer who's looking at that loan application, and he sees that, okay, this person's loan application was recommended as accept, he might care about what other people were there other people who are similar to this person who were also recommended accept. So it's a different kind of explanation, because it's more in terms of identifying samples. While in your case, it's more about identifying features, saying, okay, if your credit score was whatever, 760 rather than 740, then your loan would have been up. So there are very different ways in terms of how explanations might suit essentially the end user. And this is where we reach the toolbox. But I think before that, if anyone has any questions on this previous part, feel free to ask, or you can ask at the end, either way. No, so in deep visualization, they'll actually look inside the network to sort of see the intermediate representation and visualize those. Lime is totally model agnostic. So it doesn't care what your model is, it could be something else. It's just like, you're just taking instances, seeing what the output is from your model, and just fitting to those things in Lime. So it doesn't care what's happening inside. If you have two models that give the same predictions, it will produce the same explanation. No, so that's for the global I was mentioning. So in the deep visualization, it is mostly about visualizing the intermediate layers. It's not about fitting another model. Are there any other questions? Yeah,
it's more like a clarity question. In the definition, it says that methods or
explain.
Methods.
Right.
They're all the same. Like I said, sometimes they're different. So how do you distinguish when you're talking to an audience?
Right. Right. So the question is, people use interpretability and explainability, or at least some people use it differently. Is there a difference, and if so, what? So I'm using it more interchangeably, but generally, people who distinguish, for them, interpretability is a stronger term. And it's more of a global term. That is, if you say something is interpretable, it's more like that you actually understand the model and essentially most of the decision flow. While explainability is more used in a more local sense. That is, explain why your loan was accepted, or explain why my loan was rejected. So that generally a distinction that some people use to distinguish between interpretability and explainability. But for the purpose of this talk, I'll use it interchangeably. Yeah. Okay. Oh, so we didn't use distillation. There's the distillation didn't work actually. It actually made the tree even worse than its original performance. So I think there we essentially in the toolbox there's one method which we used, which improved it. So there was so that method is different. So no, that's a good question. So I probably didn't say that clearly. Yeah, so it was a different method which sort of reweighted inputs. And The interesting thing about that method is actually it's kind of intuitively, if you just look at it, it's opposite of boosting. The sense you weigh easier examples higher, not harder, sorry. And in the method, as opposed to boosting where you usually weigh the harder examples higher and higher successes. So if you, I think if you look at the paper, maybe you'll get a better intuition of why we do that and why that generally works. Okay. No more questions? Okay. Sir. No, go ahead if you want to. Right. So, yeah. So we go back and forth. We usually go back and forth in terms of what's useful for the final user. So because usually the first explanation is not that useful. So you try to essentially distill out what he really wants, and then from that sort of loop, you can converge on something that's that he finds useful. But like I said, in different domains, you might want completely different kinds of, even the form of explanation might be different. So even though you might give a certain kind of explanation, however accurate or however easy it is, they might still not want it. They're just used to a different kind of. So we would basically fine tune and refine it for seeing what kinds of explanations, and then amongst those kinds, what is the best sort of way. Right. So to some degree, so it depends on how far the expert is, right? So it depends on his sort of evolutionary path in terms of how much does he know about working with, say, machine learning algorithms and so on and so forth. So, right. So, so in a way, they also get trained because, in a way, so for example, right, like when you do Google search for something, say you're trying to find something, I mean, Google might be training their search algorithm, but it's very hard for my grandmother to find what she wants on Google. So in a way, you have also got trained in terms of how to better search for what you want. So generally in the interaction, it's not just about algorithmic improvements, it's also about the person getting more familiar with the space and understanding things.
So how much of that have you or your colleagues tried to represent, rather than just saying they didn't like that, I'm going to try something else? So do we say these are the types of explanations, these are the types of users? Like, I don't know whether you were here yesterday, but the MD said that he gave two criteria for two kind of necessary, but in my opinion, not sufficient criteria for getting a good explanation. One of them was whether the model predicted his expected outcomes, which I think would be hard to evaluate to begin with. But how much of that is represented someplace?
Right. So usually, I mean, through the toolkit and stuff, it's only the algorithms that are exposed. But if we are working with specific experts, we would actually, like I was saying, like in the manufacturing thing, it's very similar to the doctor case because they are, I mean, there's a lot at stake, and they want to be really sure. So what happens in that case is that we would sort of note down like what the general expectations are, or at least at a certain level, because even individual to individual, there are some sort of variations, right? So, but we would know from that, like at least that this is the class of explanations that they want. So for example, like in the engineer case, we knew that local explanations are not going to work. So you at least know like, okay, we don't have to bother about these, we'll just look at this class of methods. Now in this class of methods, given that essentially you try to understand their constraints, and those are sort of either relayed to people who would work with in the future with those engineers, or if you're the one who's working or your team, then they already know that. So they would essentially adapt based on these things, and then they would essentially create what's appropriate for that person.
So what's the best paper? I'd like to find out more
Right, so there is a paper which so the user studies won't be there in that, but it will have the stuff that I'm going to talk about in terms of essentially the types of explanations, the taxonomy, and it also has examples about, say, if you're for different personas, how different kinds of explanations might work. So the paper is, I mean, I can go ahead, maybe a few slides. Yeah, but this is the paper. So we just put it up on archive a week or so. Okay. Okay, sorry. Okay, so now this leads us to the toolkit that we just released. So like I said, the fairness toolkit was released last year, which Prasanna spoke about, also the adversarial robustness. So AI explainability is the third in the sort of list, and there's a causal inference one, which is coming, so stay tuned. But so one of the things about this toolkit is also that we have currently 8 different explainability algorithms, and I'll show you where they lie in the hierarchy that we have created. Also, this is the link, this is the GitHub link. And there is also interactive experience, which can actually take you to the GitHub. I'll show you all of this, but yeah, but this is all the information essentially in terms of what's currently there. And of course, it's open source, so you guys are welcome to contribute and use. Right. Mhm. Right. So I mean, so I'll get to the taxonomy. I mean, maybe that will clarify things. So there are different classes of techniques, right? So depending on what the expectation is. So for example, like in the engineer case, they want an interpretable model. So that's their constraint. So even if it's a little lower performing, it's of course really hard to get the exact same performance in mode because it's not, because if it did happen, it would have probably happened before. So in those cases where you know that there are certain hard constraints, you essentially just obey them and try to do the best thing possible that you can with given those constraints. In other cases where people are happy with, say, local explanations, you don't really have to compromise on the model at all, right? Because you can still keep using your original model. And you can use some of the methods that I've shown, as well as we'll talk about, to essentially create those explanations. So it just depends on what the setting is, what the setup is, and what the expectation is. Okay, so this is a taxonomy that we have created based on surveying this whole explainability, interpretability space, and also the stuff that we have. So like I said, on the interactive side, and this is also, yeah, I should also add, this is also a small decision tree, so it's interpretable in itself, hopefully. But the idea of this taxonomy is that we do not claim it to be like complete or perfect, of course, but the whole point is that hopefully it's useful in a wide sort of range of applications. And the idea is that hopefully people can, looking at this taxonomy, seeing where they are, like the gentleman here was asking me, right? So depending on what kind of explanations they want, they can use the taxonomy and reach the right leaves so that they can use the right algorithms or class of algorithms for their purpose. So at the top, we have static and interactive. Like I said, on the interactive front, the amount of work that is there is rather thin. Also, the question marks in this chart essentially indicate that we don't have anything in the toolkit currently under that category. Also, there is a legend saying what sort of modes the different things will work. So like, for example, tabular is blue, image is red, and text is green. And this shows that with essentially which of these modes this thing would work. So like you can see, so So currently we have 8 algorithms. So you can either explain data or you can explain a model. Now, the model part is actually the most popular, but you can have explanations where you're trying to explain essentially complicated data sets. So there are different ways to explain. So currently in the toolkit, we have 2 algorithms. One of them is called Proto dash, which basically will summarize your data set in a small set of instances. So for example, it will select diverse and representative examples to essentially represent your data set. So as an example, say if you take the MNIST data set, right, which I think everyone knows, which is handwritten digits, so 0 to 9. But say if you didn't know and if somebody just give you 50,000 samples, you're probably not going to look at all the 50,000. But you can use this and say, give me the 10 most sort of representative samples, and it should ideally give you like all the 9 digits, rather than just picking a bunch of zeros or ones or so on and so forth. So that's one way of explaining. The other we have for images is DipVA, which is basically what is called as disentangled representations. And the idea here is that, say if you have image data, it's in the form of pixels. Pixels are not really sort of interpretable to humans. I mean, you can't really essentially say anything about the image just from a pixel. So what this will do is essentially it will create higher level features. So for example, if you have like a clothes data set, it will create things like sleeve length and so on and so forth. So obviously it won't create the label, but it will create essentially few features. If you take, say an image, say a shirt, and if you vary that feature, you'll see that the sleeve length is increasing. So what this can do is it basically will create a few set of higher level features, some of which may be interpretable and useful. So this is one. Then we have, again, Proto dash can be used in multiple scenarios. So if you have model explainability, again, like I said, you might want local explanations or global. If we go down, say the local branch, you can have post hoc, and we have a method which is self-explaining, and essentially what that method does is that in addition to just inputs and labels, if you also give, say, for a certain domain, like explanations of what the experts have said, the method will learn the model as well as generate those explanations. So that's why we are calling it self-explaining. But it is still like, the model may not be globally interpretable, but you're creating instance-wise explanations, so it is like still under local, but self-explaining. But if you have a model that's basically you've picked and it's not self-explaining, then you can do post hoc explanations. And here again, you can do samples or features. That is, so for samples, obviously, if I'm the patient, show me similar patients. For features, we have something called as contrastive method, which will tell you, for example, if your loan application is denied, it will not only tell you which features in your loan application are sufficient for your loan application to be denied, but what minimal changes to your application would have actually made it accepted. So it will create things like that for tabular as well as image data. I'll maybe browse some of these notebooks for you guys. And then if you go down the global branch, there again you can have direct or post hoc. For direct, we have 2 rule learning methods, which will essentially generate rules, interpretable rules, that are hopefully not too many, but which will be useful for prediction. And in the post hoc, we have this method called profit, which goes actually to your question. So that's the method we use for the decision tree thing. Yeah. So we have that in the toolkit, but we don't have that use case in the toolkit because the data is confidential. But yeah. So like I said, all the question marks indicate there's nothing in the toolkit currently that covers those categories, so we welcome contributions, and even contributions in categories where we have stuff, because it's still like a rich space you can add. Now this is just a quick sort of glance at some of the classes that are there in the toolkit. So you have direct explainable for unsupervised, supervised, local black box, local white box, global black box, and global white box. So you can, if you create, say, this is more from in terms of contributions. So if you contribute, you can essentially inherit from these classes and create your explainers. So this is just a quick sort of brief sort of snapshot on how the toolkit compares with some other toolkits that are out there, and even products. Along these dimensions, so in terms of like data explanations and directly interpretable and so on and so forth. So, in a certain sense, we are like the most comprehensive. Also, one of the other, I think, cool things is that all of the algorithms have been developed in-house. So all the stuff that's there is, yeah. And this is, like I said again, this is the paper, if you want to. Yes, yes, everything is open source. Okay, so now what I'll do is, I'll just show you the toolkit. And okay, so this this is the IBM AIX360.mybluemix.net. This is the sort of the central page, and it has a similar feel. We have purposely tried to keep it consistent with the fairness one, so it has a similar look and feel. So there are, so if you do get code, you will actually go to the repository. So this is the repository, and it has information about how to install this toolkit and all sort of the details. And it also has links, information about the papers in terms of the algorithms that were contributed. And it also has some other information which may be useful in terms of, like I said, the paper, its citation, and a short sort of 35-minute video which me and one of the other authors recently essentially produced as part of one external meet. And from here also you can essentially jump to like tutorials and notebooks and so on and so forth. So, and from here, yeah, you can see that there are essentially 5 in-depth Jupyter notebook tutorials covering different sort of use cases. The first one has 3 different algorithms. And so, yeah, I would encourage you guys to look at those. So they are quite detailed in terms of, we have tried to put a lot of text. We have taken a decent amount of effort in trying to make it very sort of readable. But other than that, there are also additional notebooks which have less sort of text, but they have still they're like running Jupyter notebooks. So the top ones are tutorials, but we have like additional examples also for some of the other algorithms in different sort of using different kinds of data and so on and so forth. So what I'll do is I'll just shortly, quickly show you a demo. So this is a demo that we created for the FICO dataset. So this dataset actually is quite well known because last year FICO released this dataset, and they had a FICO explainability challenge where you were to predict for home equity line of credit. That's essentially the difference between how much you own your house and what it's valued. People want to take loans on that essentially difference. And the thing is that given a bunch of things about the person's profile, you want to essentially predict if you want to recommend the person's loan be accepted or denied. And actually, the algorithm that won the challenge is also part of this toolkit. So it was a rule-based method which won this challenge. So this was, this came out last year. So what we did in this demo is that we look at 3 different essentially personas and the different kinds of explanations they might desire and how the toolkit basically could satisfy their need. So for a data scientist, for example, For a data scientist or some higher level executive, he may not care about sort of local, just single explanations. He might care about how is some model performing at a global level. So for that, we have some rule-based methods, which will create sort of rules of this form. So this is actually an input feature in the data set. It's called external risk estimate, which is part of a person's profile. And what this plot is showing you is that as the external risk estimate increases, this model will predict that it's more likely that the person's loan should be approved. And it also shows you jumps, like it'll give you rules saying that, okay, if the score was this, then the importance increases by an additional this much amount and so on and so forth. So it'll create a very sort of transparent set of rules for you in terms of how you should actually predict acceptance or essentially someone denying it. So this is essentially, this plot is essentially a summarization of these rules. It's basically saying that initially you have some weight, and then as you reach these values, you essentially have more and more importance given to that feature, in addition to its original sort of importance. And the color shows that this is basically positively correlated with someone's loan being approved. So green means positive, red means negative. So these are some of the features in the data set. They are sort of semantics. I can quickly browse, but basically these were some of the things that are interpretable for people from FICO or finance. So this is for the whole data set. Yeah, this is for the whole. So in this case, it's not about explaining a particular instance. The model is built for everything. And what this is showing is how that model is interpretable, because you can essentially break it up or disentangle it into these kinds of plots as well as these kinds of rules. Right. So it is giving you an idea of that, yes. So it is saying that if you have a person who say this quantity is greater than 75, then those group of people will most likely pay back their loan with higher sort of probability than people say who have less than whatever 69 or some other number. So it is.
But does it then let me figure out what an external risk estimate is? Like, how do I figure out what my external risk estimate is?
Yeah, so this model is catered towards the person who's actually deploying the models. So this sort of explains. So this is not for an individual who's applying for a loan. So I'll get to those. Okay. So this is for a persona who is basically, I'm say some head data scientist and I want to deploy this model. I want to be sure that it's not making some random decisions and it actually matches my intuition. A little bit similar to what the doctor situation there. Because I don't want to deploy something that's making arbitrary decisions. So this is for that kind of a person, to get an sort of a global view of at least, I mean, you might make mistakes on a few people, but in general, does it make sense? So this is for that kind of user.
This is a rule-based model?
Yes. Yeah, then you wouldn't be able to do. So this is selling this rule-based model, that why this is appropriate for this kind of setup. So you could also have a tree or something like that, but this is the one which is there in the toolkit. So. Yes, absolutely. In this case, yeah, it just turns out that they're monotonic, but they don't have to be. So you could have something that says, for example, that, okay, I mean, it's not there in this example, but maybe in the notebook there might be an example. But it's possible that it might say that, oh, if it's greater than 75, then reduce by some amount. Okay. So this is from sort of someone who wants a global view. The second persona we look at is a loan officer, right? So he's seeing these applications being given either acceptance or denied. So he wants to know, like, is that reasonable or not? So the kind of explanation that he might want is that, can you show me similar people? say to Alice, whose loan was approved, or to Bob, whose loan was denied. And that might give the person more confidence in terms of what decision was recommended. So if you say click on Alice, so it'll come up with, so there's some text which you can read, but basically, I can summarize it. It'll come up with essentially outputs like these. So these, obviously these names are made up. It won't come up with the names, but it'll show that for Alice, given Alice's profile, these were the other profiles, say 3 profiles that if you wanted, that are very similar to Alice's profile, and and Alice was approved. And also these 3 had also paid their loan. Yeah.
But how do we know how those people are similar?
Right, so that's indicated based on this shading that you see.
You don't have a notion of the 10 characteristics that made them similar.
No, so these are the characteristics on which I know those are kind of black box for us because these are sort of the domain that it was deployed in. For them, this is interpretable. And I'll show you actually when I go to the notebook, I'll show you the actual text descriptions for each of these fields. So they want an explanation in terms of these factors. There's some, I don't know, some number like 24 or something like that. So what this explanation is saying is that, okay, Alice's loan was approved, and it probably in this sense made sense because these 3 people also paid their loan. And there is a weight parameter which shows also how similar a particular person is to the person in question. And it will also show which features were exactly the same as that of Alice. So that gives you more confidence that these other profiles were very similar to Alice, and they also paid their loan, so the approved status is probably okay. Oh, so these are given. These are all given. So so in your data set, right? So these are the 24 input features, and the output is given if these people's loans were accepted or denied. So that's how you. What the method is doing is that given a specific individual, because there's so many possibilities, right, of other people also, it is actually picking the most similar people who are also diverse enough in the sense it's possible that 2 people are similar in very different ways. So it takes into account those aspects. So it'll try to pick the most similar but also diverse group that essentially matches the person that you're interested in. So this is another kind of explanation. So the main point of this is to show like diversity of explanation. So, and for denied also you'll get a similar kind of thing. Okay, so now the third is like a bank customer. So say like you have applied, right? And in this case, mostly if your loan was approved, you wouldn't care what the reasons are. Mostly you would care if your loan was denied. So what this method does is that, and what you would probably care more is there a way for you to actually have it accepted in the future, or are there any actionable ways of doing it? So what this method does is that it will not only highlight features which sort of led to that decision, but it will also tell you things like this, saying that it will try to find the minimal set of features that you have to change by the minimal amount, which will, with 100% guarantee, change the prediction of the model. So actually this method in terms of local explanations, that's why is much more tighter than say Lime, because with Lime you're fitting just the predictions and you're hoping that those features actually map to what's happening in the model. But this thing guarantees that if for the person in question, Jason, his profile, these 3 factors had values of 65, 52, and whatever the last value was. But if it changes to 72 and 68 and 3, we give you 100% guarantee that Jason's loan would have been approved.
Do you make any kind of consideration on some things you can change?
Right, so you can do that. So here we are using all 24 because we are not the domain experts, but if someone tells us that, okay, the person can only, and it's very reasonable, right? Like if someone says reduce your age, I mean, there's no way I can, but they can, yes, they can sub-select and say what's actionable, and you can only focus on those factors. But it can, the point is that it can create these kinds of explanations and also give you feature importance in terms of which might be the hardest to change, even though, because these things are not normalized, right? They're in the original. It might be much harder to change a smaller difference for a certain feature than a larger difference for something else. like age, for example, right? If I say even go back 6 months, it's like everyone wishes, but so you can create these kinds of explanations, and so this is for a third kind of user, and it will generate sort of this is similar form of explanation. So for example, Anne, there's only one thing that she has to change, and Julia, again, some 3 things that they have to change, and the point is that it'll automatically figure it out. And also this method can work for even multi-class problems. So it'll find which class to go towards automatically. Okay, so maybe since I showed you the, okay, FICO demo, I'll jump to the notebook. But just before that, maybe since I'm at the web page, I'll just show you this stuff. So there are also a lot of resources. Like we have tried to make it educational, like the tutorials are educational, but also other stuff like paper links and so on and so forth, as well as write-ups. And there's a Slack community, which also I encourage you guys to join. So if you go here and if you say request an invitation, we already have, I think, it's been just a month, but we have almost, I think, 70 or 75 members. But you can join and you can ask questions, even just generic explainability questions and stuff. It doesn't have to be about the toolkit. Okay, and then there's also like guidance, like, so we have to update this tree with the one I showed you, but basically there's more guidance material in how to pick the right algorithms and stuff. Like I said, we have put in effort to make it as educational as possible. And then there's some glossary of commonly used terms and what they mean and so on and so forth if somebody's interested. Okay, so let me go to one of the tutorials. So since we are talking about FICO, let's stay on FICO. Okay, so this is the tutorial notebook, which once you install everything and all, it should be available. But even if you don't, if you just click on the website, this thing should show up and you can download it. And like I said, like I showed you, there are sort of 3 personas that we were trying to cater to in this case, and 3 algorithms which sort of provide different forms of explanations. So if you go down this notebook, so here are essentially the input features that were there, and this is some text description that FICO provided of what these features mean. So some are less transparent than others, but this is what we have. So, and also the last column is interesting, which helps you to do a sanity check on some of the model as well as the explanation. So what the last column is saying is that, so they, besides giving what they mean, they have also told us, I don't know why this thing. They've also said how do these features sort of relate to the final person's loan being accepted or denied. So what monotonically decreasing means is that if external risk estimate essentially reduces, the probability of rejection increases. Or if external risk estimate increases, probability of acceptance also increases. I know in terms of terminology, it's a little confusing because you would think higher risk means lower this, but that's, I mean, those are essentially the features they use. And they tell you how they should vary with the target. So you can use these in sort of validating your models as well as your explanations. So for the data scientist case, like I said, so I'll just quickly go over this. I'll mostly go into the CM part. We have these rule-based methods. There are 2 rule-based methods. So it will learn a model based on features. Here's also like, this is just to show like the data and so on and so forth, just so that you have something initially there. And then once you train the model, so you can see that you've trained a model and this rule-based model had a training accuracy of 69.65. And then it will give you essentially the coefficients for each of these factors. And what you see is that There are a lot of these coefficients, but the way you interpret them is those plots. That is, you can aggregate them and produce the plots like I showed you. So for like external risk estimate, essentially if you collapse those rules, it will create plots of this form. That is, if you increase it by this amount, it's going to affect your loan being basically accepted, keeping everything else constant. And you have this for other features too. So like things that are, yeah, I'm just trying to see if there's something that's sort of non-monotonic, because someone asked in this case, but it's possible. But I don't know if something is going down and then going up. I guess not in this case, but it's possible, yeah. So that was for the rule-based model. For this prototypical explanations, again, you can essentially load the data set, and we're just showing some sample applicants whose risk performance, or essentially whose loans were rejected. And then these are some, essentially the distribution of some input metrics like external risk estimate and trades and so on and so forth. So I'm just going pretty fast on this, but so that because I think there are 10 more minutes, so I can show you some other stuff more closely and also take more questions. But basically, you're building a model, and then you call this explain. So for a person with ID 8, whose prediction was basically acceptance, that is good. You want to see if that's really justified. So this is his profile. So those are the values for that person, and we want to find similar but diverse individuals to that person. And what it'll do is basically it'll essentially create a table like this, showing so the first column is the original person, and all the other columns are actually all of these columns are the people who are similar to the person in question. So in the demo, I showed 3 people here, so you can choose how many you want. And so here it shows 5. And the thing is that the algorithm, the good thing is also it's non-randomized. So if you pick 5, the first 4 will be the same as if you picked 4. So there's no randomization. And then these are the sort of relative importances of each of these people being similar to that person in question. And then it'll also do like a feature similarity, saying, if you want to understand more, like, so 1 means like the feature is exactly same as the original person, while anything close to 0 means that it's very different. And then we have also sort of summarized whatever I was just saying in this, like as an explanation. So as to why, as to how that person's decision could be justified in terms of acceptance. Okay, so this is similarly for the bad. Like we just chose a good candidate and a bad candidate, and it's pretty similar. The last thing is the contrastive stuff, which is more from, like I said, from the customer standpoint. So here, again, we have the HLOC data set. We show a few applicants. Again, the same thing in terms of showing some features. And then there's some normalization and so on and so forth. We train a neural network classifier. And then we try to compute contrastive explanations for few people. So this 1272, we want to create an explanation for his prediction. So what we see is, so we want to see first, okay. So his credit, so he was going to be rejected, which is what you see, prediction X is basically for this guy, he was going to be bad. And the algorithm will try to see what minimal changes will make it good, and these are basically the highlighted changes. So if these 3 things change to these values, then the model would have predicted him as his loan should have been accepted. And if you actually look at these features, the direction is also as you would want them, based on that monotonically decreasing or increasing column I showed you. So this, And like I said, the guarantee with the method is that there's a 100% guarantee that this XPN, if it finds a pertinent negative, it is going to lie in a different class. So at least you have that assurance. So there may be, it's not going to sort of make an error in terms of the final decision. So these changes will definitely produce the change. Of course, there may be other ways of doing it, but this will definitely produce a change. So if this thing, if the explanation actually is not amenable to you, one thing is that it could also indicate that maybe you have to change or debug your model, because that means it is not really respecting some of these constraints. Now, how you do it is a totally different question. Yeah, so this is, so the way it's different is that, so the PN is that it's a constrained, so I'll show you for images. So we say that you can only add stuff. And so it's like a constraint, in a way, so we have an optimization problem. One way to solve it is like a constrained attack. One way you can solve it is a constraint. But there are also sort of other aspects to it. So this is the PN part, but there's also, so we call them as pertinent negatives. And this term I think I got from the medical literature, because many times, say for example, and this will become clearer, I think, the MNIST example is that doctors and all use this a lot. Like, so for example, say if you go with some symptoms of cough, cold, and fever, right? So the person might say, okay, you might have flu or pneumonia, but then they might ask you, did you have chills in the night, or did you have mucus? To which say you answer no, then the doctor might say, okay, you have probably flu rather than pneumonia. So the point is that not just the things that are there, but things that are sort of critically and minimally not there are also very important in decision making. And so what this method, this will become clearer actually in the image case, how this method is doing this. So you're trying to find minimally absent stuff that will actually produce a change. So there are two aspects for this explanation. So one is that. The other is we want to see that what sort of minimal stuff will actually keep the same prediction. So what it's saying here is that if you even zero out all other features, and these three features, if you basically take them to this value, this person's loan would have still been accepted. So together it gives you a more sort of complete feel, like a more rounded explanation. Right. So in general, yeah, if the decision boundary is extremely jagged, yeah, it could be that you go a little bit and it changes. But in many sort of practical situations, we have seen that it's at least somewhat monotonic over a range. Yeah. Right. I mean, like I said, you can still use it to debug models, right? Because if you're not happy, but that anyway, I think, is the application of local explanations. Because just because you give me a good explanation, I'm not going to start trusting your model, because there could be a million ways in which it could go wrong, right? But you can use, it's useful in one direction, in the sense that if you find something that's unacceptable, then you can actually try to fix the model or use something else, or at least it can point towards relevant sort of loopholes. And actually, some of that, I think in future work, I'll talk about what we're currently trying to do. So yeah, just quickly, just to make that thing clear, maybe rather than the tutorial, I can show you that too, but I'll just quickly show you an MNIST example in terms of what I mean by the pertinent negative and positive. I think that should make it clear. So here, right, so on MNIST, we apply essentially the same method. And now you want to explain why this, so this image was classified as a 3 by the neural network, okay? So the question is, why is this a 3? So given, I mean, in the interest of time, I'll just go directly to the explanation. And so the kind of explanation that it will generate is of the following form. So it won't delete anything for the pertinent negative. It will say that, okay, this is a 3 because this line was absent. Because if this line were present, this would actually be classified as a 5. But also, only if these pixels, which are highlighted here, were present in this 3, it would still be classified as a 3. So it is giving you sort of what is minimally sufficient in your input for you to recover the same sort of decision by your model. But also, what if you sort of what should be minimally absent so that the decision is maintained? In attacks, you usually just add and delete all at the same time. And obviously, the pertinent positive part is not present. And there are other ways also to make this the explanations more realistic, which we do, is that you can actually train like an autoencoder or some kind of manifold on your training set so that you don't make random perturbations. So you force the changes to go along that thing so that you actually create realistic digits. So that's, and yeah, and quickly maybe I can just, show you, like for more complex images, I don't have time to tell you how we did addition here, because it's interesting for black and white addition, defining like in terms of increasing a pixel value is fine, but for colored images it doesn't make sense, because if I just increase some, firstly you have 3 channels, and if you just increase some values, it will just create a smudge. So there's some interesting things that we do so that the addition is defined in an interpretable way for complicated images and so on and so forth. I think, so you can read the paper that's at the link, but just to quickly show you, this is the kind of image it can create. So this person was classified as not smiling and something, so on and so forth. And it will basically, and that's an input image, and the method will actually generate, so this is not an image which is there in the data set, it has actually generated this image. And it has basically added teeth. And it's saying he was not smiling and he has raised his cheekbone. So it will create an explanation of that from saying. So it's not just pixel level manipulation. It will say that this person was not smiling because his cheekbones were too low or teeth were not showing. Sorry? Yeah, it generated it. So we learned a generator and then on the original data set, and then we gave these sort of constraints. I mean, it's actually interesting how to optimize, and yeah, it's a very interesting, because you have to create also a realistic image, right? So it doesn't work all the time, obviously, but it works many times. Right. So the thing is that so the PN part is, since it's like addition only kind of constraints, what we have seen is like in the MNIST example, for example, even without any sort of additional guidance, it actually created pretty interpretable things, like interpretable perturbations. So I mean, we haven't had time, but we were thinking if like a positivity constraint and stuff, maybe certain kinds of neural networks are robust in terms of if you constrain the type of attacks that you can do, but we haven't studied that in detail. So it might be interesting to see. But here it's like we are actually using some higher level features. So I don't have time, so I won't. But I think you can look at, so this paper is also on archive, and it's in the list. If you go to the website, you should find a link to it. But you can create such interpretable sort of explanations. Okay. So in terms of, sorry. Oh, okay. So there are obviously a lot of possible directions, interesting, firstly improve methods and so on and so forth. But I'll just touch upon a few interesting directions. So one thing is causality, like bringing more sort of causal connections rather than random correlation. So like, for example, like smoking causing cancer and so on and so forth. So we're trying to sort of marry some of the causality stuff with this explainability stuff. I mean, it is, I mean, many people consider causality to be like the holy grail, but it itself is not sufficient for good explanation. So for a very good example is, for example, say, I was just telling this to one of my friends. Say if you have a barn and you have hay in the barn, and say the barn caught fire, right? So there are a lot of causal factors for the fire, like there's oxygen, but there are a lot of barns with oxygen and so on and so forth. There's hay, but there's a lot of barns with hay. But if you see like a burnt matchstick in the barn, then you can say that that actually is the cause, or that actually led to the fire. So the thing is that it's not enough to have, because you can have many causal connections going through, but I think if you want good explanations, it is much more targeted than that. It has to be much more sort of filtered out. And contrastive, actually, what I showed is one way of doing it, because you're saying that you have two sets of things, and what is really the difference between these two things. The other thing is that we are trying to do is, like I said, like the local explanations in a way can only sort of help. I mean, it's useful for that specific individual, but from a global model perspective, it is really useful in one direction in terms of debugging, but not really trusting the model. So what we are actually trying to do now is somehow to use these contrastive explanations to essentially extract a Boolean model from, say, a neural network or arbitrary models. And this also can have some interesting things for inductive logic programming and so on and so forth. So actually, there's a way, if you look at our pertinent positives and negatives, if you take each feature, you can think of it as, I mean, there are some steps, but basically as a literal. That is, because what we're saying is this is present, this is present, this is present, then this is the class, but this should be absent, this should be absent, and this should be absent. So you can actually view it as a Boolean formula. And so for every training sample, we can actually run a contrastive thing and get such Boolean formulas. And if you take actually an OR of these clauses or some combination, it's a huge Boolean formula which will have 100% faithfulness on the training set with your original model, because of the guarantees that I said, that it's 100% accurate in terms of. But the question is generalizability. Can you basically, firstly, the Boolean formula will be very huge. So firstly, can you shrink it? And the most important thing is, will it generalize to test instances? Because if you are able to do that, then you can basically extract Boolean formulas, they may be large, from like neural networks or arbitrary models. And even if not interpretable, because they might be large, they'll be transparent, because you know exactly what went into the decision making to create a particular prediction. So this is some of the stuff that we are actually trying now, and it'll be cool if it actually works. So reinforcement learning is another thing where you have multiple agents interacting and so on and so forth. And is there a way to basically extract essentially another sort of maybe MDP, like a Markov decision process, where you have few states and few transitions, but the states are abstracted enough that they are interpretable, as well as the transitions are, in a way, what we are looking at is sub-goals. Because that's how, in general, we humans learn, in terms of, before getting into the details, like say, for example, if you're learning chess or something, I mean, say how to mate with a rook, you might say that, okay, like try to reduce a row or a column for the king, I mean, and then reduce space, and then you can. So these are like sub-goals, because you're not really telling the actions that, okay, move this to this exact square and so on and so forth. So we are also trying to see if we can, I mean, for reinforcement learning, but I think it would work for any sort of sequence generation kind of thing, where you can actually create lessons. And if there's something interesting that you can actually teach, which people did not know, I think it would be very interesting. Even for chess, because with alpha 0 and all, we already know, I mean, like getting a better player is not really the challenge. It's more about, I mean, better system is not the challenge, but what can we learn from maybe some of its strategies and so on and so forth. So it might be interesting to discover such things. And then there's also one thing which we are trying to explore is that most of this explainability stuff are search problems. So can we basically use quantum computers to enhance some of these things? So that's one of the sort of going directions too. And that's it. Thank you. Any questions? Any more questions? Yeah, go ahead.
From the toolkit, the number of algorithms and the subdivision or metrics, there's only two metrics on faithfulness and monotonicity.
Right.
So are those the best metric for all the algorithms, or is other metric you're using for each of the algorithms?
No, they're not the best. We just put two, like one of them is very popular and the other one we thought was reasonable, so we put those. They don't really judge the quality of the explanation in terms of understandability. They check more like how accurate is the explanation. So there's a lot of stuff you can still add like there. So they're by no means like the metrics or anything like that.
Post-hoc methods which interact at the macro level of say the confusion matrix, where I want the false positive rate to go down. I'm okay with some trade-off with respect to false negatives. What is the implication with respect to the model?
Right, so improving models is something that we are currently working. So, so there are different ways, like that's one metric, like you can do TPR or whatever. So it's not something we have done. And I think most of the work in this space the current state is that most of it is not catered towards improving an already existing model. It's more about sort of deciphering what's there. But I think essentially improving is the most natural sort of future sort of direction which is interesting. The thing is that it's not that simple in terms of improving because there could be many you can try to improve one thing, but then something else might go off if you have some other constraints in terms of model complexity and things like that. But yeah, it's interesting.
Good talk. Have you thought about, so I'm totally behind the explainability, but have you thought about the comments that if I explain how the model works, I could expose to hackers how they can hack the model?
Right. So I think in most, I think robustness thing, why it's a challenge is that in security or something, it's assumed that you have like most of the things will be known in terms of what system is there, but still you cannot hack it because it's just too hard to essentially hack the system. So even though you might have certain explanations that come out of the system, it should be the system should be designed such that you can't essentially leverage those in a cheap way, because nothing is impossible. I mean, you can hack anything. It's just about how expensive it is. You just have to make the cost high enough so that it's not worth it for someone to do it. So it's yeah. So how that is designed is I think a more meta question than just explainability. So you have to design the sort of the system in such a way that the cost becomes higher than the sort of payoff.